So one of the challenges with a VVT engine is for a given speed and a given manifold pressure, you can have a dramatically different VE depending on your cam positions. This is the same tool that I was showing earlier, where normally you would expect a given curve, in both of these windows. Now you have this big distribution that's quite wide in terms of its ratio here. Explaining our cam reckoning convention here, larger numbers both for the intake and the exhaust mean toward overlap. So on the intake, lower numbers means retarded, higher numbers means advanced. On the exhaust, lower numbers mean advanced, higher numbers mean retarded. So if you graph it in this space, this is least overlap in this corner. This is greatest overlap in this corner. This is the parked position, roughly for the 2015 plus Coyote engines. In our convention, roughly 50 degrees on the intake cam and 0 on the exhaust cam. So what I'm going to do, I'm going to turn on a filter here. So now, for instance, so I've got my mouse cursor. Actually, let me turn off the hover. So I will position it with the scroll bars here to the sort of parked position. So in the parked position, you see you have a conventional distribution where you have a line when you look at each one of these slices, and that's just, use your imagination. It's just a conventional engine at this point, and this is this would be the, roughly speaking, the kind of VE map that you would need for the parked cam position. So that's wonderful. That's great. But the issue is when you move, when you deviate from that sort of reference position, then you have a dramatically different VE versus map, for instance. Here you can see that at low engine speeds, this particular cam position set yielded less VE here and more VE at the high positions. And you can see that as I move the focus of the cam positions over in this graph, you can see the coverage at a given cam position pair. So here in the in this corner, I basically did a larger mapping. Here in the 0, 0 corner, the least overlap position, I did a mapping. This is the parked position. This would be maximum overlap, and you can see over in the coverage map, you can spot the max overlap because of the fact it just doesn't achieve high manifold vacuums, at the lower speeds. And maybe more to the point for this discussion, what's at the high overlaps here over in this corner, what you see is you have a dramatically different slope to the VE versus map relationship, and things are quite peaky here, because of the effect of the exhaust tuning and things like that. If you are back down in the least overlap position, then things are much more smooth, but overall, low volumetric efficiencies with such a retarded IVC there. But anyway, this shows you the sort of challenge of trying to be tolerant to an entire range of cam positions with a VE model, because of the fact let's see. Sorry, I was trying to figure out why the filter didn't turn back off. But anyway, so how do you do that with a VE model? I tried a couple of different things, one of which was based on the idea that, I'll turn this back on. So if you move along the line of a constant overlap, you can see if you watch the this VE versus RPM, you can more or less offset it to get it about right, and there's not a dramatic change in slope of the VE versus map. You see more of a change in slope of the VE versus map with varying overlap. So I don't have incredibly dense data here to show you, but as you're if you sort of keep the same overlap center line and then you change the magnitude of the overlap, when you look at this curve, you see a big difference in the map versus, or VE versus map relationship, and it's even more pronounced at lower speeds. So if you move this down to say 1500 RPM, you have so at least at lowest overlap, you have a very flat relationship here. The VE doesn't change much with map. You go to the other end of the spectrum, you have a massive slope in terms of the rate at which VE falls off as a function of differential pressure or pressure ratio across the engine. So the challenge is, how do you account for that? So one of the things that I've been trying here, playing around with, is so I have a reference VE map that's essentially based on the VE at the parked position in the event that there's a failure or something like that. That's just what I arbitrarily chose as the reference. The reference could be another cam position set, but basically the reference VE map is for a given constant intake cam position, constant exhaust cam position. Map out the engine VE as a function of speed and manifold pressure. That's the reference map. Then I have two compensations that I've tried to solve for here. One of them is a VE offset as a function of RPM and your intake position phasing. I did that because of the fact if you're running a single cam engine instead of a dual cam or twin independent, you might only use this position offset or position based offset. So again, in this context, 0 means most retarded intake position, 70 is most advanced intake position. So if you look at, let's just say, pick out 1500 RPM, that's a low enough engine speed where retarding any retard of the intake cam is going to cause your VE to fall off, and that's what you see here. You see a pretty strong gradient. And then on the second map is an overlap sensitivity. So basically, I'm looking at the relative slope of the map, or the VE versus map, at different levels of overlap, and trying to characterize the relative slope as a function of engine speed and overlap. And the way I'm defining overlap in our convention here is it's just your intake cam position plus your exhaust cam position, because of the fact that both of those are increasing in the direction of overlap. So what I'm calling overlap is just the sum of the two, but that's sort of arbitrary. That could be rescaled. So that would in effect try to compensate for the change in slope that you see, like between high overlap and low overlap. So moving in this direction, the change of the slope can somewhat be calibrated out by tuning this overlap sensitivity map. So it's the reference map, the phase offset, which I'm tying to the intake position, and then the overlap sensitivity. Those three maps, I combine those parameters to try to approximate the VE with what I've called a three-map strategy. So I'm going to turn this on so you can see that as I move my cam focus, or my cam position pairs, what it's doing is it's applying those three maps to generate my VE curves here. So the blue line is no longer from this map, and the green line here is no longer from this map. These VE values come from the three map model. So you can see how that fits as I move around, and it's not a perfect approximation, but it's decent, I would say. At least it pushes things in the right direction. It's really the easier thing to do would be to use a mass flow sensor or a different way to estimate it. But in the context of not having that available, this is sort of the next best thing that I've managed to come up with at the moment. What I also have in addition, so what the reference VE map compensated with these two map values, what they don't make up for, I'm thinking about using potentially a radial basis function model to essentially make up the difference between, or make up the error between actual versus the three map model. Because, for instance, you can see this is probably a good point here. There's a tuning effect that you can't compensate out with the three map model, or you can't compensate well, and that's also, let me see. Yeah, so in some areas where there's a strong VE gradient, it would be nice to have another factor to try to iron that out. But let me see if I can find. Here's a good one. Yeah, of course. Yeah, that's exactly what this was showing. But as you move away from the higher overlap positions, let me move the focus back here to something where I have a bit more data. As you move away from the higher overlap positions, their relative tuning peaks are a little bit more mild. And you can see that, as I'm moving the cam around, or the cam position pairs around, it's because of the fact that the three map models, you have variability of these coefficients as a function of RPM. It's also warping the base map in sort of a strange way to try to make it fit the measured data. So here's a good example where I have some good support. I should have here in this corner as well. Yeah, so that's not so bad. There's the parked position. But you can kind of see how the three map strategy. Now I should add, I don't have the radial basis function. Right now I'm using 0 points because I haven't done the fit for this generation of engine. So right now I'm only using the three map strategy, not using the radial basis functions at the moment. So that gives you a general idea of how that three map strategy fits like I said, it's not perfect, but I just wanted to get some mechanism of having a sensorless, I shouldn't say sensorless, a mass flow sensorless estimation of the VE, or of the airflow. And obviously with the VE we would be using a MAP sensor, manifold pressure sensor, for the main load index. But anyway, that gives you an idea of what I'm looking at, or what I'm evaluating at the moment. If you have any interest in actually playing with this interactively, I can send you the executable and the data that I've taken, if you have any interest in doing that. Otherwise, let me know if you have any thoughts on ways to make this better, or if you have any insights into other potential mechanisms of modeling a good VE in the absence of a mass flow sensor that we could potentially use. This is obviously something that's it's a little bit abstract for most of our users, but I can't. I haven't been able to get a better fit with a simpler model. I'll say that. I did develop some mechanisms to fit these coefficients in an automated way. Right now, and obviously I'm not a very good programmer or anything like that, but to optimize these two maps with the roughly 500,000 points that I have, it takes on the order of hours to converge on a solution for a best fit. And like I said, that's not perfect. But anyway, that's the general 3-map strategy that I was looking at. I can send you the formulas if you're interested in looking at it, but otherwise I would like to get feedback on what you think of it.